All right. Thank you for your introductions. Welcome to Engineering 117 again. We just finished talking about the syllabus. Now I'm going to um, go delve into the course material. Okay, starting with chapter 9.1 in the textbook. Okay, um, we are done with 117 introduction and syllabus. I want to quickly talk about Phasor domain review. Okay, so let me point you quickly to these resources on Moodle where you can watch 9.1 through 9.11, all the lectures made available to you by Professor Russ Tatro, and also YouTube videos from my 2020 summer course in Engineering 17. Okay, if you go to this Engineering 17, uh, you should be able to find your way to chapter 9, which is sinusoidal steady state analysis. So what I'm going to do in this lecture is to keep it probably short and to give you a summary, because this is something you should have picked up from Engineering 17 as well. And by the way, this is the agenda that we discussed so far. This is what we have done so far. Excuse me. So this is what we discussed so far. Before I start the material, let me quickly mention this, that when you're on Canvas, you want to click on the account, okay, and notifications, okay. When you click on notifications, let me leave my student view and demonstrate. When you click on notifications, it'll take you to a page where you can click the bell icon next to the announcement. I want you to do that because all the important information, relevant information from time to time will be made available as announcement. Once you click the bell icon, you will be notified via email about that. Okay, so that's something I want you to pay attention to. If you did not already, sign up to Moodle and then try your homework one today. Okay, just to make sure you have access to it the way I wanted it. Okay, with that said, with those housekeeping stuff out of the way, let's quickly review chapter 1. Chapter 9, I meant to say. Okay, chapter 9, sinusoidal steady state analysis. Okay, and like I mentioned, this is supposed to be a review of the material from Engineering 17. Okay, let's see. I'm going to give you a summary view of the chapter. Okay, maybe I'll do a couple of examples. Um, However, the main learning for you in this chapter is going to be through the videos that I just showed you on YouTube and on Moodle. Okay, so sinusoidal analysis. Sinusoid, we could be talking about cosine or sine wave, is a very, very useful input signal. Okay, it's a very, very useful wave for us, and it's a stand-in or it's a representative. Okay, it's a representative signal that mimics a lot of real world signals. Okay, or in other words, if you understand how your circuit responds to a sinusoid signal, then you can extrapolate that understanding. You can extend that understanding to apply to a wide range of real world signals. Okay, does that make sense? That's the idea of more or less the Fourier transform. Okay, let's see. What's the big idea of the Fourier transform? Can anybody remind us what a Fourier transform is? We look at Fourier transform in this course a good depth. The idea is any wave that is repeating itself, okay? Any wave that is repeating itself at a set frequency, if it is repeating, okay, this wave is a repeating wave at a set frequency. The idea is I can represent this as a summation of a bunch of sinusoids. As a bunch of sinusoids. If a wave is repeating, that can be expressed as a sum of bunch of sinusoids. That's the idea of Fourier series, Fourier transform. Okay, the idea that I guess I'm trying to drive is sinusoid is a fundamental wave. If we understand sinusoid, it'll be easy to understand any other kind of repeating signal in the real world. Okay, so this is what we will be doing in this class. First, we will understand what a sinusoid is, what its mathematical representation is in time domain, okay, in polar form, and in polar, also called phasor, also in rectangular form, okay, in three different forms. Once we do that, we will also, so that's first chapter, we will understand 9.1 is understanding the representation of sign. Okay, then we will 9.2 is about this phasor representing the sign in time domain, polar form, rectangular form. Then we will go on to understanding what happens if I have a circuit. Okay, if I have a circuit, some kind of R, L, L, C, R, C, some kind of um, circuit, and I apply the input of a sine wave, how is the output going to look like? Straightforward, isn't it? So this is going to be the thrust of this chapter. First of all, we understand the representation of sine wave. Then we examine how the output is going to be when the input to a circuit is sine wave. Okay. Then we will also look at KCL, KVL, and node analysis. All these kinds of techniques in sinusoidal, in time varying inputs. When the input is sinusoid. Okay, how does the circuit respond when the input is a sinusoid? How do you apply the KCL, KVL, the frequency domain, that kind of interesting stuff. But the main thrust again is if you have a circuit and you're interested in applying a signal that is time varying. In this chapter, we will try to understand how the output is going to be, okay, when you apply a time varying signal to the input. Everybody with me? Questions, please. Questions so far. Okay, like I mentioned, I'm going to give you a summary view. Okay, this is a preview of what to expect in this chapter. Okay, so let's begin with 9.1, the sinusoid. Okay, the representation of a sine wave. This should be straightforward to you. But before we even go into sinusoid, let me give you, um, spoiler alert. Okay, when you apply a time varying signal to an electrical circuit, The output has two components, has a transient response, has a steady state response. Okay, so in other words, when I apply an input, something like that, a time varying input, okay, the output is going to look something like this. Okay, you see, there are two aspects to this output. The first aspect is where the input, where the output is varying, and then the second aspect is where the output is constant. Okay, so that's the steady state aspect. Okay, and then this is the transient aspect. Okay, these are representative, these are not exact waves. Okay, so there is a time decaying aspect, that's the transient aspect. Okay, after some time, the time varying aspect is going to decay. Then there is going to be a steady state response. It could even be a sine wave. Okay, but the idea is the output is going to be a function. Okay, the output is going to be a transient response plus a steady state response. Okay, steady state response meaning that it persists. Transient response means with increasing time, it decays. Okay, in this chapter, we are going to talk about, spend a whole lot of time understanding the steady state response. Okay, so when the input is a sine wave, what is the steady state out? Okay, so that's something we want to um, park to one side of the brain. Okay, all right. So like I mentioned, sinusoid, it could be cosine or sine. Okay, it's a representative wave. It's a stand-in used as a representative or stand-in for a lot of real world signals. Okay, a lot of real world signal. Okay, so we'd like to understand the sinusoidal analysis. Okay, a lot of real world time varying signal. Let's see. Let's begin by drawing the sinusoid, which you should be familiar from your high school or from your engineering 17 courses. Let me simply do that, okay, as a representative sine wave. There you go. Okay, so let's do this as a representative sine wave and try to understand the different aspects of it. Okay, so first thing I'm going to do is probably do that. Okay, this is a cosine wave. Okay, so on the x-axis, I have time, and on the y-axis, I have the voltage, or I could even have the current. Okay, let's see. Straightforward. This is again, like I mentioned, a review. There are different properties of the sine wave. Okay, the example sine wave, the representative sinusoid that we look at in this class is a cosine. Okay, in this class, we are going to be spending a lot of time talking about the cosine. Okay, cosine omega t plus phi Vm. Okay, that's the expression for the sine wave. Okay, let me see if I can make this a bit bolder. Okay, here it is. Okay, here is the expression for the cosine wave. Okay, let's try to identify the different aspects here. So there is a VM term, which is also called amplitude. That's the maximum voltage in either directions. Okay, that's VM over here. Okay, then there is the omega. So this is VM, right? That's the maximum voltage. Then there is the omega term. Let's see if I can use a different color for that. Then there is the omega term, which is represented by the time period. Okay, the time period between two peaks or two valleys is the capital T, and 1 over capital T is F, and 2 pi F is omega. Okay, this is the angular frequency. F is the frequency in hertz. T is the time period in seconds. Okay, F is the frequency in hertz, and omega is in radians per second. Okay, so we are looking at the different aspects of the sinusoid. Okay, and the little t is the variable t. Now, how about phi? What's this guy? Who can tell me what this phi represents? Anybody remembers what that phi represents? Angle. How do you mean, Srinjay?
I was talking about like sometimes they have like the you can use it as an angle for like radians.
Yes, that's true. Um, Correct. It's expressed in angle. My headphones are going to die out on me in just a minute. So when they do die out, I'm going to switch my headphones and find a different set of headphones. Okay. Now, let's see. Think of this way. Let me clean this up a little bit. Okay. So there is your VM. VM is amplitude. Okay. And omega, oops, omega is the angular frequency. Okay, and I pointed them out to you, the physical phenomenon that they represent, right? Now, the phase really is this guy. Okay? When it is moving left and right, the time translation, I'm going to show that in a different color, maybe this color. Okay, this represents the phase. Okay, let's see. Maybe I can duplicate this, right? There you go. Okay, so if you look at the red wave, okay, and the blue wave, they're exactly the same, except that one is delayed compared to the other. Okay, for example, if you look at the time t equals to 0, okay, the red wave has reached its peak value, right? Whereas the blue wave did not reach its peak value. It probably has to wait a little longer before it reaches its peak value. Okay, so in other words, the phase angle phi simply represents if it is offset. Okay, if you remember, the sine wave looks like this. Okay, it starts at 0. Sine 0 is 0. Sine 45 is 1 over square root of 2. Sine 30 is half. Sine, you get the idea, right? So sine 0 degrees is 0. Sine 90 degrees is that guy. And sine 180 degrees. You get the idea. So this is 180 degrees, and this is 360 degrees. Okay. On the other hand, cosine wave looks something like that. Duplicate. Oops, nope. I wanted to do that style. Your cosine wave is simply, please bear with me. Let me go to Bluetooth and connect to the other's headset. Okay, let's see. Okay, so the green wave is a cosine wave. The blue wave is a sine wave. Okay, the only difference between them is that they're offset in time. Okay, and you can translate that time into degrees. Okay, so there is 180 degrees, there is 270 degrees, there is 370 degrees, so on and so forth, 360 degrees, so on and so forth. So this is 180 degrees, so on and so forth. So the idea is this notion of left and right shifting that is captured by phi. Okay, does that make sense? So this blue wave, for example, is not at its peak when time t equals to 0, unlike the red wave. Okay, so that phenomenon of left and right shifting is captured by the phase. Okay, and you can express it in terms of degrees, angle. Okay, so those are the characteristics of sine wave. And of course, there is V RMS or IRMS of a sine wave, root mean squared, which is simply Vm squared over square root of 2. Okay, Vm squared over square root of 2. Vm over square root of 2. I'm sorry, the root mean squared. Okay. Now, the textbook talks about, elaborates on the idea of root mean squared. Okay, root mean squared, if you have a function of t, how do you find the root mean squared of that? Okay, so the first thing you want to do is to square the function, integrate it over one full time period, and average it. That will give you the squared and then the mean. But then you still have to do the root aspect of it. That's where the square root comes in. That's the root. Okay, so if you want to do the same thing for a sinusoidal wave with a cosine omega t, if you do it formally, you will find out that this root mean squared value of a sinusoid is Vm over square root of 2. Is everybody with me? So these are the aspects of a sinusoid. Okay, so phase angle and frequency, and then amplitude and VRMS. Okay. Now, by a show of hands, how many of you can hear me with the new headphones? Perfect. Thank you. You can load your hand. Okay. So this is 9.1 sinusoidal wave. Okay. The textbook talks about an example. We have a little bit of time. Maybe we can go into a quick example. Okay, it's going to be silly for those of you who did engineering 17 recently. The textbook says, example 9.1, okay, the peak value is given to be 20 amperes, okay, and the time period between successive peaks is given to be 1 millisecond. Okay, I read the textbook, and then I'm distilling the information that the textbook gave. Okay, and the textbook says that at t equals to 0, the value of I is 10 amperes. Okay, and then there are some, these are given. And then the textbook asks you to find out the frequency, da. Okay, and then what is the angular frequency? Easy. What is the expression for I of t? Okay, and then of course, what is VRMS? This is what the textbook asks you to find out. So in effect, the solution that you're after is little I of t is what you want to express. You want to write it as Im cosine omega t plus phi. Okay, let's see what the unknowns are. We don't know, well, we do know the value Im. Okay, that's the peak value, that's given as the peak value here. Okay, so that is straightforward. Then we still need to find the value of omega, but we know we can find the value of omega from time period. Once we have time, we should be able to write 1 over t, which is f, which gives us f. Once we have f, we simply multiply 2 pi f to get the value of omega. Okay, how about phi? This information about phi is not readily available to us, but we can extrapolate, we can extract that information from here. Okay, the problem says Im cos omega t plus phi is equals to 10 amperes at t equals to 0, right? That's this guy, that's this information. I at t equals to 0, maybe I should write it as little I, okay? Little I at t equals to 0. The value of the current at t equals to 0 is given. So we can plug in the value of 20 here because Im is given to be 20. Cos omega times t, t is 0. So all of that term is going to go to 0, okay? Plus phi equals to 10 amperes, which mentions that cos, which gives us that cos phi is equals to 1/2, meaning that phi equals to 60 degrees. Okay, you can cosine inverse of cosine inverse of 60 degrees. Now you get, now you have all the information. So this is an example, a simple example. I of t is equals to 20 cosine omega is going to be, if you plug this in, it's going to be, f is going to be 1000 because 1 over 1 milli. So 2000 pi times t plus 60 degrees. Okay, you get the idea. And then you should also be able to look at the examples, okay, and solve such interesting problems and simple problems, going back and forth between this time domain expression and extracting the different values. Okay, what you want to remember is Vm, omega, and phi are the characteristics of the sine wave. Vm represents the peak value, omega represents the angular frequency, and phi represents the offset at time t equals to 0. Okay? Now, that's 9.1. And 9.2, like I mentioned, is sinusoid steady state response. Okay? And probably I'm not going to spend a lot of time talking about 9.2, sinusoid response. And I'm particularly interested in steady state. Steady state response. Like I mentioned, sinusoid response could be transient, okay, and then steady state. In this chapter, we are only interested in steady state response. Okay, we are interested in steady state response. Okay. So we know certain characteristics of steady state response. Okay, when the input, okay, when input is a sinusoid, okay, I can tell you for a fact that the output is also sinusoid. Okay. Then when the input is a sinusoid of input frequency omega, then okay, the output frequency is also going to be omega. Okay. In other words, for linear circuits, okay, the input frequency is going to be the same as the output frequency. Or in other words, if you have a linear circuit, that's not going to change the frequency of the output input, the incoming input wave. Once it passes through the linear circuit, its output frequency is still going to be same. It's going to remain unchanged. Okay, so that's the second characteristic. The third characteristic that I'm interested in is the amplitude of the input wave is probably almost always not the same as the amplitude of the output wave. Okay, let's call this as simply A. Okay, sometimes we call this as A, sometimes we call this as Vn. Okay, when you're writing a voltage signal, voltage of T is capital Vm cosine omega T plus phi. When you're writing a current, you could be writing as Im cosine omega it plus phi I, simply showing that it's a voltage equation and the other is a current equation. Okay, so in effect, these terms, the peak values, when I want to represent them, I use amplitude. I like to call them as amplitude. And the idea is the input amplitude may not be the same as the output amplitude, and the input phase may not, in most cases, the same as the, may not, in most cases, be the same as the output phase. They're different. They will more likely be different than they're likely to be the same. Okay? Questions, please. Questions so far. So that's the summary of what your output is going to be. Okay? So let me put it in a different manner. Okay? Take a circuit, take a linear circuit. Doesn't matter how many resistances you have, how many capacitors you have. It's a circuit built out of some resistors, some inductors, and some capacitors. Okay, some black box circuit, mystery circuit. Okay, when you apply a sine wave input to this, the general characteristics are that the frequency input and the frequency output are the same. The amplitude input is going to be different from the amplitude output. the phase input is going to be different from the phase output. And what else? If the input is a sinusoid, you know for a fact that the output is going to be sinusoid. Okay, so as much we can definitively say about the steady state response, steady state sinusoidal response. By response, I simply mean the output. What is the output in response to the input? So don't get thrown off by the nomenclature, response. It simply means the characteristics of the output. Everybody with me so far? Does this sound familiar from your engineering 17? Questions, comments, concerns? Okay. We have about 20 minutes of time. Okay. And I promised I was going to give you, and of course, please go back and look at some example problems and also the videos that I posted on YouTube. Let me also go through the next step, 9.3, the Phasor. Okay, I'm going to make it absolutely dead simple for you, very, very simple for you. I'm going to make an observation here. Okay, the input frequency is the same as the output frequency. So there is no need for us to spend a whole lot of time calculating the output frequency because it's going to be the same. So the only things that are going to change are the amplitude and the phase. Amplitude input is not the same as the amplitude output. Okay. Phase angle input is not the same as the phase angle output. Right? So this gives rise to the idea of a phasor. Okay, so our effort is to collect the amplitude of the input and the phase of the output and be able to estimate the amplitude of the output and the phase of the output for the given circuit. Okay, so in other words, this combination of angle and amplitude, okay, that's a combination that's going to be useful for us to estimate the response. Okay, so what we are going to do is this. Okay, in this class in engineering 17, you must have seen that the time domain representation of the sine wave or a cosine wave can be represented in its phasor form. Okay, so this is the time domain expression. Okay, then there is the phasor form, which is simply a collection of the amplitude, okay, and the phase. Okay, the information about the phase. If you can curate that information, okay, we don't have to worry about omega, right? Because that's the frequency that does not change between input and output. So this representation, this collection of amplitude and angle is called the phasor. or the polar representation. Okay, so what we will do is we will go back and forth between these three domains. Time domain, you will switch back and forth with the polar form, and that you will switch back and forth with the rectangular form. And that you will switch back and forth with the time domain representation. Okay, so if we clearly understand how to switch between these three forms, okay, they represent the exact same sinusoid function. Okay, the sinusoid function can be represented in a time domain form, or it could be represented in a polar form, or a rectangular form using complex numbers. Okay, rectangular form or complex numbers. Okay, what we want to remember is that all of these three domains are really meant to make our life easy. Okay, so if you are finding it incredibly difficult to go between these three forms, then you're probably missing something somewhere. Okay, it should not be. It is meant to be dead easy for us. Okay, I have about 15 minutes of time. So I'm going to talk a little bit about the relationship between the three forms, the time domain, okay, which is mostly in the cosine form, trigonometric form, okay, the polar form, and the rectangular form, okay. I'm going to make an effort to show you how they're representing fundamentally the same quantity, okay, fundamentally the same phenomenon. But before I do that, what questions do you have, please? Questions so far? Everybody with me? Isaac, Pratham, Jose, Jesse? What's going on, guys? Isaac is happy. Okay, good. So, Jesse, did you want to chime in? Okay, sure. Thank you. Now, what I want you to do is I'll be picking on you. There is no such thing as a wrong answer, like I mentioned. Don't be uncomfortable to talk. Think out loud if some thought comes to your mind. I really don't want you guys to get into a silent mode throughout this semester. Okay, I hate to be talking at you. Okay, but if we have to consider breakout sessions, we can do that. But I would strongly encourage you to ask questions, share your wisdom with your folks, or chime in with any concerns you have. Okay, so here we are looking at a Cartesian plane. The effort is to show the equivalence between these three forms. Okay, once you see that these three forms are pretty straightforward, they're representing the same fundamental quantity, then you should have no problem at all in shifting between these three forms back and forth. Okay, so let me point you that the horizontal axis points to you that the horizontal axis is the x-axis and the vertical axis is the y-axis. Okay, and by Euler's identity, you can call this as the real part and this one as the imaginary axis. Okay, please bear with me with these names, real axis and imaginary axis, but we are pretty used to the Cartesian plane, right? The x-axis along the horizontal plane, horizontal axis, and the vertical axis is y-axis. Okay, now let's say I want to denote a point. Let me make a bigger point here. Okay. Let's say I want to represent that point in the Cartesian plane. Okay, there are a bunch of ways I can do that, right? So the one way to represent that is using its x and y coordinates. Okay, the distance from the x-axis and the distance from the y-axis. Okay, so this is x and this is y. So this is x comma 0. The distance from the y-axis is that guy, or this part is the real part, the real axis distance. Okay, and then the distance, the y coordinate represents the imaginary, the distance that we traveled along the imaginary axis. Okay, let's say these values are 1 and 1. Okay, then let's say you're starting your journey here at the origin and you want to give directions to your friend to reach 1 and 1. And what you would say is, let's see, Kara, start walking eastward and walk east for 1 mile and then head north for another mile. Then you will reach your destination. That's the pink spot. Because Kara is trying to reach that pink spot, right? So one way for her to reach would be you can give her directions in terms of the x-axis and the y-axis. That's the rectangular form. Okay, if I have to represent that, it will be x plus jy. Okay, jy meaning imaginary axis and the real axis. Okay, so that's the idea. Now, the exact same information you could also convey to her
I don't think we have audio anymore. I think your headphones might have died.
Okay, guys, can you hear me now?
Yes, we can.
Okay, so what were we last discussing? What was the topic that we were discussing the last when the polar form? Okay, so you get the idea, right? So how do you think I arrived at this square root of 2 um, for the amplitude or the magnitude? Okay, so everybody with me, let's get back to the idea that Kara could start walking at a 45 degrees angle to the horizontal and walk route 2 miles along that direction, 45 degrees, and then she could reach her destination. Okay, so these two are fundamentally equivalent. That's the equivalence there. I ended up with the square root of 2 because of Pythagoras theorem. Okay, if I have a right angle triangle, x and y are the coordinate, x and y are the sides of the triangle, and this guy is square root of x squared plus y squared. Okay, so that's what I know from my Pythagoras theorem, and then that's what gave me the square root of 1 squared plus 1 squared square root of 2, the angle 45. Okay, how do I know this is 45? This is an isosceles triangle with two sides equal. So one of them is 90 degrees. So the other angles have got to be equal 45 degrees. So basic trigonometry, basic mensuration tells me that the angle has to be 45 in a right angle isosceles triangle. Okay, everybody with me so far?
Yes.
So the idea is Kara walking 1 mile towards east and 1 mile in the northward direction is exactly same as she walking square root of 2 miles at a 45-degree angle. This is called a rectangular form. Rectangular form. This is called a polar form. Okay, this is called the polar form. Now let's see, let me see if I can copy this information. Copy this and show you the equivalence in terms of let's see, okay, in terms of the trigonometric expressions. Okay, I'll clean that up as well. So this I mentioned is the x-axis, and this is y, and this is angle phase. Okay, then it's straightforward to see that cosine of phi, and let's call this as square root of x squared plus y squared. Okay, cosine of phi is the adjacent side to theta or phi divided by the this guy x squared plus y squared. Okay, let me simply call this as amplitude A. Right now, sine of phi by definition in trigonometry is the opposite sine to phi divided by A. Okay, and tangent of phi is by definition opposite side of phi by x. Okay, now we have an equivalence of all the three forms. If you wanted to get the x plus jy form, so this is x plus jy, right? X is the x-axis plus jy. Okay, x plus jy, dang it, I wanted to do this guy, no. X, if you want to get to the real part, which is x, then all you have to do is the real part this imaginary number e to the j theta, or your sine wave, a real part of your e to the j theta is a times cos phi. Okay, the imaginary part, that's e to the j theta, e to the j phi. Okay, so you get the idea that e to the j phi is cos phi plus j sine phi. Okay, so this guy multiplied by this guy will give you y, which is the imaginary part here. Okay, that's the imaginary part, a to the sine, a times sine phi. Okay, and if you want to get this value phi, then phi is tangent inverse of imaginary part over the real part. So the real part is x, imaginary part is y. Okay, now let me summarize in the 1 minute that I have left, or that I don't have, in the 1 minute that I don't have. X plus jy is a complex number that represents a point in the Cartesian plane that could be represented as a angle phi, or it could be represented as a sine wave as well. Okay, this a is square root of x squared plus y squared. Okay, angle phi is again tangent inverse of imaginary part over the real part. Okay, however, if you want to get the value of the real part, then you would do a times cosine of phi, and the imaginary part is a times sine phi. Okay, so you have a mechanism of relating the three forms. Okay, this is the polar form, this is the rectangular form. Okay, this takes you from rectangular to polar, and this takes you from polar to rectangular. Okay, and then of course, given a sine wave, you know how to get the polar form. Just look at the amplitude and the phasor phase. Okay, so it's that simple, it's that straightforward. If you are given a sinusoidal wave, you simply convert it into its phasor form. Okay, and then you can go to rectangular form and do all the gymnastics. And in the next class, I will come back and show you how easy it is to work on different circuits when you have sinusoid inputs, if you get this part down. So I'm sorry to have taken a couple of minutes of your time over the allotted time. So you're free to leave at this point of time. If you have questions, let me stop the recording. If you have questions, you're welcome to ask